So work, power and energy, this is session number 6. So yesterday we got cut off in the lecture in between because of the power situation. So let's quickly discuss. Yeah, that's okay. I will explain that whole part again. So we were talking about potential energy and internal conservative force. Okay. And its relation with internal conservative force. Okay. And the general expression we saw that in any system, the change in potential energy is negative of work done by internal conservative force. So the examples of that we saw, first was the spring elastic potential energy of the spring. Okay. So we had seen that delta U of the spring is negative of work done by spring force. So that becomes integration of kx dx from initial to final, because work done by the spring is given by minus kx dx integrated from initial to final. Okay. So from this formula, we got the absolute potential energy of the spring as half kx square. So this was the first of the two examples we had seen yesterday. And next up, we had seen about gravitational potential energy. So this we had seen for a specific condition for a body of mass m near the Earth's surface. That is, its height from the Earth's surface is very small compared to the radius of the Earth. So for that, we had seen that the change in gravitational potential energy is equal to mg delta y, where delta y is the vertical component of displacement and g is of course acceleration due to gravity. Has a value of 9.8 meters per second square, approximately 10 meters per second square. So these are the two important formulae so far that we've seen about potential energy. Right, so I'm going back to the example that we had seen at the end yesterday, because we had got cut off in that. Okay, so hope these two formulae are clear. Please ask me if there's any doubt. Okay, so now let us see this example. So a particle is projected from the ground at a speed of 50 meters per second at an angle of 53 degrees with respect to the horizontal, and g is equal to 10 meters per second square. Yeah, it's fine. I'll explain that. Okay. So I want you to find the speed v of the particle when its height is 20 meters. Okay. Find the speed at a height of 20 meters. Okay. So use this concept. Use work energy theorem. Okay. And take the earth plus the particle as your system. Just try this out, people. Yeah, so that's why I'm saying, na, we are doing the same question now. I will send you the notes of yesterday's thing, Kanish, so don't worry about that. Okay. Let's concentrate on this question at the moment. It's the same type of question. So see, what is happening is, it's going in a projectile motion like this. Okay. So suppose we are talking about the speed over here. Okay. When its height is 20 meters, or again on its speed, on its way down, suppose the speed is V2 like this. So how we can find this V1, V2? Use work energy theorem. Okay. So you can see over here that for this system, there is no external force because only mg acts. Okay, only mg, which is the internal conservative force, acts during the projectile motion. Okay, non-conservative force is zero. Okay, so change in kinetic energy plus change in gravitational potential energy is zero. Okay, so let's say this is B and this point is C. So if we apply A to B or A to C, whichever one we apply, we get the relation that half mv square minus half mu square plus mgh. This is the change in kinetic energy. This is the change in potential energy. That should be zero. So our relation here becomes that v square is equal to u square minus 2gh. So v is equal to square root of u square minus 2gh. So both those speeds will be the same. Okay, both during the ascent and during the descent. So that will be slightly greater than 40. Okay, so hope the application of work energy theorem is clear here. Just make a note of this. Okay. Okay, this is clear now. I'll just take you back to yesterday's lecture notes once. Okay. Okay, so same thing. We're discussing about gravitational potential energy, mg delta y. Change in gravitational potential energy is mg into change in vertical coordinate. Okay. And the last part, as you can see, is the same type of problem we have just discussed. So if you like, you can just note this down quickly. Okay, so this part is done, I hope. Let's come back to today's notes. All right, so now that we are familiar with basic applications of the two potential energy formula, the spring potential energy and gravitational potential energy. Now let's start looking at problems where there are external force also involved. Okay. So next example we'll see is like this. So back to spring mass system. So initially the block is at rest. Okay, attached to a spring in relaxed state. Mass of the block is suppose given to us as 5 kilograms and the spring constant is given to us as 20 newtons per centimeter. Okay. Now a constant horizontal force starts acting on the block like this. of magnitude, let's say 50 newtons, starts acting on the block. This is a smooth surface. So find the acceleration just when F starts to act. Secondly, the speed V of the block when the extension of the spring is equal to 2 centimeters. Okay, so all these things we have to analyze over here. Okay, so I want you to start with part 1. Just make the free body diagram and explain to me how we will get the acceleration when the force just starts acting. Then we'll come to part 2. Part 1 is nothing to do with work by energy. It's just free body diagram because you have to find the acceleration. So acceleration doesn't come from work energy. Acceleration comes from free body diagram and Newton's laws. Okay, so what happened is very simple. The first part, the acceleration initially x is equal to 0 for the spring. Na? So spring force is 0. So there's only this force acting. Okay. So let's say the acceleration is a naught. So a naught is just F by m. The force we applied is 50 newtons and the mass was 5 kgs. So it starts off with an acceleration of 10 meters per second square. Okay. But after some time, by the time this has happened, this has become L plus X. Now the spring force is there. Okay. So the acceleration would have reduced. So in this picture, let's say the speed of the block is V. Now you compare this with the initial picture. Okay. So work energy theorem. Take your system as the block plus the spring. Okay. So on the block, F, mg and normal reaction, these are all external forces. Non-conservative force is not there. Okay. And the spring force, that is your internal conservative force. Okay. So when you write your work energy theorem, work done by external force plus work done by non-conservative force is equal to change in kinetic energy plus change in elastic potential energy of the spring. So this will become work done by F. This will be the application of work energy theory. Okay. Because work done by mg is 0. Work done by normal reaction is 0. So apply this over here. This was the initial state. This is the state after some time. So E to P, what is happening is work done by F will be F into X because F is a constant force. So F into X is equal to half mv square plus half kx square. This is your work energy relation. From this, you will get V as a function of X. So you can find out V when X is equal to 2 centimeters. All that you have the data given. The force was 50 newtons. The spring constant was 20 Newton per centimeter. The mass of the block was 5 kg. Okay, now, so understood this now. As the block is going from this state, where its speed is 0, x is 0, and we start applying the force to this state after some time, where the spring has got extended by x. Speed is v. You have half mv square plus half kx square is equal to fx. This is the application of work energy. Change in kinetic energy plus change in potential energy of the spring is equal to work done by F. Okay. So now we want to find out V when x is equal to 2 centimeters. Okay. So half into 5 into V square plus half into K, which was 20 newtons per centimeter. So they write it as 20 into 10 raised power 2 newtons per meter, okay, into x, which is 2 into 10 raised power minus 2 square. This is equal to the force, which was 50 newtons. Right. So 5 by 2 V square plus this will become 4 into 10 raised power minus 1, I think. Yeah. So this should be equal to 1. Okay. So 5 by 2 V square is 1 minus 0.4 or 0.6. So V square is this much. Okay, so this is the application of the work energy theorem. Same thing which I've shown above. So we wanted to find V and acceleration. Okay. So I found out V. Now you have to find the acceleration also. Yes, that's good. That's correct, Antesh. So you'll see that the acceleration would have reduced to 2 meters per second square. But what is the direction of the acceleration? It will be along the positive x-axis. So at this moment, the force of 50 newtons, which is acting, and the spring force Kx. So this Kx is equal to 40 newtons because we are taking x is equal to 2 centimeters. Okay. So this combination will mean that the acceleration of the block is in this direction. So F minus Kx will become ma. So the acceleration will be 2 meters per second square along the direction of F. Okay. Now you have to repeat this whole thing in the next part for x equal to 4 centimeters. Sorry, 3 centimeters. B and A when x is equal to 3 centimeters. So there's a particular reason I've selected the 3 centimeters. We'll discuss about that in the end. So just work this out now. Note this down and repeat this calculation for x equal to 3 centimeters. So let's repeat this calculation for this. नहीं minus नहीं आएगा बेटा. V will still be positive. See, 5 by 2 V square. Because see, V here is the magnitude of a velocity. No? So See, understand here, v is the magnitude of a velocity. Okay, so we won't take plus minus. It's the speed now. So speed will be the same, which you are getting in 2 centimeters. So it's an interesting thing, and I'll tell you why that's happening later. Okay. But what about the acceleration? Now, what about the acceleration? You can see that the spring force that is becoming how much when x is 3 centimeters? It's becoming 60 newtons. So it will have a deceleration. Okay. So it will have an acceleration of 2 meters per second square, but along negative x-axis or opposite to f. Yes, -2 like that. Okay. So we will understand this again when we are analyzing the last two parts, why this is happening like this. So find the maximum extension of the spring, and last part, find the maximum speed of the block. That is the value, beta. 0.24 ka square root is approximately 0.49 only, Prince. Yes, very good, Anmol. That's correct. Okay, so see, so far what we are observing that when x was 0, the block had an initial acceleration of 10 meters per second square. Okay. Then we are seeing that by the time x is becoming 2, its acceleration is becoming 2 meters per second square. Okay. Now we'll also see that at the instant when x is equal to 2.5 centimeters, you can see x equal to 2.5 centimeters पे acceleration 0 हो जाएगा, because kx will also be 50 newtons and f is also 50 newtons. So acceleration is 0. Okay. And when it crosses this point, For example, when x is equal to 3 centimeters, we saw it has a negative acceleration, 2 meters per second square backwards. Okay. So what is happening is the speed now starts decreasing. So at some stage, the v will become 0. This is when x is maximum. Okay. So what is happening from here to here? V is increasing. Okay. From here to here also V is increasing because acceleration is positive. But after that, what happens? V is decreasing because acceleration is negative. Here also V is decreasing. Okay. So at maximum X, V should be 0. The block should momentarily stop. So that is the concept we'll use now. Okay. So going from this diagram to this diagram, we will see that work done by F is equal to change in kinetic energy plus change in potential energy of the spring. So Fx is equal to half mv square plus half kx square. So in this formula, if we substitute v as 0, x is maximum. At x equal to the maximum value, v should be equal to 0. So substitute that over here. So we'll get f into x maximum is equal to 0 plus half k into x maximum square. We get 50 . Okay. So we will get two roots. One root will be 0, that is the initial state. The other root will be this, when x is maximum. So at this point, you'll see something very interesting. It also has a symmetrically backward acceleration. The backward acceleration will be the same as the forward acceleration initially. It will be 10 meters per second square. If you do the calculation, you can see. Okay, very good, Anmol. So can you tell me what is the concept you've used for calculating the Vmax? At which point of time V is maximum? What should be the value of X when V is maximum? Yes, very good, Beta. That's correct. नहीं, x equal to 0 पे प्रिंस देखो क्या हो रहा है, the acceleration is maximum but the speed is 0 ना. So all the information is in this series of diagrams. You can see क्या हो रहा है, 0 से 2.5 the speed is increasing और 2.5 से लेके 5 तक what is happening, the speed is decreasing. So at which point of time, yes, it will happen when the acceleration is 0. That's correct. So when the acceleration is 0, what is the value of x? It is 2.5 centimeters or f by k. When the acceleration is 0, x is 2.5 or f by k. So at that moment, the speed is maximum. So in this above work energy equation, if I substitute x as 2.5 centimeters or f by k, I will get the value of v, which is maximum. Okay. So there are two ways of understanding this. One is from the free body diagram method, which you've just done. So fifth part, we want to find out v max. So if we just look at that series of diagrams, now we will understand this. So let us see the block at various different stages here. Okay, now all this while we are continuously applying the external force. So we'll understand the whole motion actually, not just this thing. Okay. So in this picture, the first one, our x is 0, okay. U is 0. So it has a maximum acceleration of 10 meters per second square. Now in this picture, let's say x is equal to 2 centimeters. So it has a v, which we had just seen was 0.49 meters per second. But also it has an acceleration in this direction of 2 meters per second square. Okay. Now when we come to this stage where x is 2.5 centimeters. So at this point of time, f is becoming equal to kx. Here f is greater than kx. So acceleration is becoming 0. So v is becoming maximum. So this is this thing we'll use for this, okay? Because after this, what is happening? F is becoming less than kx. The moment your x becomes more than 2.5 centimeters, like here, for example, when it is 3 centimeters, okay, it's still having a v in this direction, but that v is now reduced compared to the maximum because the block is now decelerating. Okay. it's a deceleration. Here it was an acceleration. Here it was accelerating. Okay. And so much so that by the time it reaches x equal to 5 centimeters, okay, v becomes 0. So x becomes maximum. But also it has the maximum deceleration. Okay. So this position, okay, and this position, they are like the two extreme positions. So at extreme positions, v is 0 and magnitude of acceleration is maximum. Okay. Whereas this one here, this is the mean position. At this position, what is happening? V is maximum. Okay. And acceleration is 0. So what will happen after you come to this point? Now it will have a V in this direction because this acceleration. So by the time it comes back to x equal to 2.5 centimeters, it will have a V of again 0.49 meters per second and the acceleration of 2 meters per second square. But here to here, it is again accelerated motion because the net force is direction and the velocity is direction coinciding. So next picture, by the time we come to, sorry, this is 3 centimeters. Because you can see the symmetry of this point and this point. Again, by the time we come to 2.5 centimeters, okay, B will be maximum value, A will be 0. So you're back to mean position. Then by the time we are at 2 centimeters, sorry, now the acceleration will be of opposite direction. So by the time we come to x equal to 0, B will become 0. But A naught is equal to, so we are back to the extreme position. Okay. So this will be the oscillation of the block. We keep going back and forth between x equal to 0, x equal to f by k, or 2.5 centimeters, to x equal to 2f by k, or 5 centimeters. Okay. So every time it is at these positions, v will be 0. Every time it's going through the mean position, v can be in either direction, but it will be maximum. Okay. And here, it will have an acceleration like this. But at the mean position, acceleration will be 0. This will be the oscillation of the block. So this is the free body diagram method to analyze. So you can see that V is going to be maximum at this position. V is going to be maximum again at this position. So that is when x is equal to 2.5 centimeters. So V will be maximum when A is 0. It is at the mean position. Okay. Or F equal to Kx, or x equal to F by K, which will be 2.5 centimeters. So in the work energy relation, substitute this. Substitute x equal to 2.5 centimeters to find V max in the work energy relation. So this is one full cycle of oscillation. You don't need to draw the diagrams, friends. I will be sending you the notes, so it's fine. But you just need to understand this series of diagrams. So as long as we keep applying this force now, alternately the block is accelerating, decelerating, accelerating, decelerating between the position x equal to 0 to x equal to 5 centimeters. And as it's going from 0 to 5 and then back from 5 to 0 and then back and forth, every time it passes through 2.5, it has the maximum kinetic energy, so the maximum speed. So make sure you understand the series of diagrams and now just apply the condition on the left hand side which I've given for Vmax. So apply that condition to the work energy relation and tell me the numerical value of Vmax is. Now find the maximum speed. So what is the value of Vmax you are getting? Anmol, you have got it, but the others calculate the value of Vmax and tell me. verify the value. Okay, people, let's just verify the value of the maximum speed. So you can see here that so 5/2 into maximum speed square plus this into 2.5 into 10 raised power minus 2 square should be equal to 50 into 2.5 into 10 raised power minus 2. Okay. So 5/2 Vmax square plus 6.25 into 10 raised power minus 1 should be equal to 1.25. Okay. So 5/2 Vmax square should become 1.25 minus 0.625. So from that you will get yeah, so I think you should be getting Vmax as 0.5. Just check the calculation. That's what I'm getting. Okay. See, this will become 2/5 into 1.25 minus 0.625. So that is 2 into that is so this calculation. Yeah, but Anmol, you should be getting the exact value of 0.5. Na? Just check your calculation once. I'm getting the exact value of 0.5 meters per second. Your concept is correct. Okay, Anmol, just check the calculation once. Okay, so this is the maximum speed. Okay, now there's another way of understanding all this also. Okay, so the other way to understand this maximum speed and maximum extension is to analyze the kinetic energy as a function of x. Yeah. So we analyze this, the kinetic energy is like this. Okay. So the kinetic energy as a function of x, you can see it's a quadratic function. Okay. The kinetic energy is like this type of a function, where A is equal to F, which is 50 newtons, and B is equal to half K, which is newtons per meter, like this. Okay. So you can see that this is like, you can factorize it like kinetic energy is like this, where A and B's values are this. Okay. A is equal to 50, B is equal to 10 raised power 3, like this. So if you analyze as a graph, the kinetic energy versus distance or extension of the spring, you get a very interesting result, which helps you justify and understand all these things. You can see this type of a graph now. It is like this. It's a parabola which has two roots. You can see roots are x equal to 0 and x equal to a by b, which is going to be 5 into 10 raised power minus 2 meters or 5 centimeters. Okay. So these are the roots, 0 and 5 centimeters. Okay. And kinetic energy can't be negative, so it will not go beyond this. So you can see this is your maximum x, therefore. Whereas the maxima will always occur at the midpoint of the roots, because this is the vertex. So the maximum vertex of the parabola, quadratic function has a parabolic graph, is at midpoint of roots. Okay. If the roots are alpha and beta, okay, so the vertex has an x coordinate of alpha plus beta by 2, which in this case is 2.5 centimeters. So this should be 2.5 centimeters. So that's another way to understand mathematically why we are getting the maximum speed at the vertex, or 2.5 centimeters. Okay, so from this you can analyze that maximum extension will be 5 centimeters, whereas the maximum speed is at x equal to 2.5 centimeters. That is the vertex point. So this is another way of analyzing this. Okay, so just make a note of this also. Yeah, I'll show the previous working also on one. Okay, so in this example, what we are having is that there is a smooth horizontal surface. Okay, smooth horizontal surface like this, which ends in a slope. Okay. So this surface eventually it becomes a smooth slope like this. Okay, so this is all frictionless. And at the end over here, there is a wall to which a spring is attached. Now a small block is released from this position A. By the time it comes somewhere here, let's say its position is B, and then it's going to hit the spring like that. Okay. So the height difference between these two positions that is h. Okay. So a block of mass, let us say 2 kilograms, is released from rest from the position A. So the height is given to us as 20 meters. Take g as 10 meters per second square. So first part, find its speed v at the position B. And second part, given that the spring constant is 15 newtons per centimeter, find the maximum compression of the spring. Okay, so this you will see is an easy question because you can just conserve energy. You can see what is happening is because there is no friction. Okay, there is no dissipation of mechanical energy. Normal reaction will not be doing work because it always acts perpendicular to the instantaneous velocity. So first, what is happening from A to B, your gravitational potential energy is decreasing and it is converting to kinetic energy. And from B, as it eventually hits the spring and starts compressing the spring, again that kinetic energy is converting to potential energy of the spring. So it's just conversion of one form of mechanical energy to another with overall conservation of mechanical energy. So first gravitational potential to kinetic, and then later kinetic to elastic potential energy. It's a very simple question. Just try this out. Yes, people, I'm waiting for the answers. It's a very easy question. Yes, correct, people. Very good. The speed will be 20 meters per second. mgh will be equal to half mv square, and then half mv square will be equal to half kx square for maximum extension. So we'll get the maximum extension, sorry, maximum compression as 40 centimeters. Okay. So what you do is A to B, you look at this change in kinetic energy plus change in gravitational potential energy will be zero, because work done by normal reaction is zero. So that means there is neither any work done by external force nor any work done by non-conservative force. Okay. So mechanical energy is conserved. So half mv square minus mgh is zero. So v is equal to root 2 gh, which is equal to 20 meters per second. Okay. Then let's say from B to C, we can look at, just think of it like this, that it's a simple case of a block moving with speed v, and then it's going and compressing the spring. When its speed becomes zero, the compression of the spring becomes maximum when speed of the block is zero. So let's say this is B and this is position C. So B to C, we can say that the change in kinetic energy plus the change in elastic potential energy of the spring is zero, because again it's a frictionless surface. Okay. So minus half mv square plus half k x is maximum value square is equal to zero. So from this you will get x maximum as v into square root m by k, which you can then substitute as 20 into square root of mass, which was 2, divided by the spring constant, which was 50 into 10 raised power 2. Okay, so this will become 20 by 50 or 0.4. Sorry, 0.4 meters. Okay, so that will be the maximum compression of the spring. So these are the values. Okay. Okay, so with this we are done with the basic applications of work energy theorem. Okay. Next time we will be discussing more applications of work energy theorem and also the concept of instantaneous power. That is, rate of work done by a force is called the power developed by it, or it is defined as the power developed by it. Okay. So we'll discuss those things in the next lecture. Meanwhile, please continue with problems from HC Verma for work energy chapter. Okay, now you can cover till about question number 30 or 35. You can cover these questions with the basic formula and applications of work energy theorem that you've seen. Okay. So that's it for today's session, people. Wish you all the best.